minutes are a little out of order. We're doing that time. Oh, good. Good 15 minutes. Okay. All right. So there's a modification another modification we need to talk about for static equilibrium, which is, what if we have, say, a moving container, right? The best example would be in your car. Okay. Imagine you've put your fish tank in the back of the car because you're moving and you need to transport your fish from your old house to your new house. Put your fish tank in the back of the car. Oh no, the fish tank's a bad idea because that's a bad example because that'll be sloshing around. You've got your fridge. Yeah, that's better. You've got your fridge in the back of the car, right? And you don't want your fridge to fall over and be smashed. Okay. So at some point, in order to drive your car from point A to point B, you're going to need to accelerate and decelerate. So all the conditions for static equilibrium, or both the conditions for static equilibrium we've been talking about, work perfectly fine as long as we are in an inertial reference frame. So inertial reference frame, of course, is when the acceleration of the center of mass of whatever object is in that inertial reference frame is equal to 0. It can be moving at whatever velocity it's moving at, and as long as you don't get close to the speed of light, all of our classical mechanics stuff works. We will talk about special relativity in a special class, in a few classes, after we do gravity, just for fun. Don't worry, it won't be on the test, except maybe next credit question. As long as we're in this inertial reference frame where the acceleration is equal to 0, it can be at whatever velocity we need to be at, and our conditions for static equilibrium work just fine. So if we got our fridge in the back of our truck and we're driving down the freeway at a constant speed, well then we just look at the conditions for static equilibrium like we normally would to see whether or not that fridge tips over. But in order to get up to that constant velocity, we need to accelerate up to it, and later we need to decelerate when we get close to our destination to bring ourselves to a stop. So when we're accelerating, of course, the acceleration of the center of mass isn't going to be 0 anymore. So we're going to need to modify our condition for static equilibrium. And the reason we need to modify our condition for the conditions for static equilibrium is because when you're in your car and you hit the accelerator, you feel a force pushing you back into your seat. When you hit the brakes, you feel a force pushing you forward. So when we are in a non-inertial reference frame, that acceleration of the center of mass is not equal to 0, and we see a new force. Right, that force we feel when we hit the brakes or accelerates. Now our conditions for static equilibrium will have to take that into account as well. So our condition for torque stays the same. Torque center of mass equal to 0. But our condition for forces changes to force center of mass equals mass of the object, acceleration center of mass. Okay. So now those forces don't have to cancel out to be 0, they have to add up to match the acceleration that we have in that new non-inertial reference frame. Okay. Hopefully that's pretty clear. Why doesn't the condition for torque change? Well, if I imagine I have two forces on an object, right? And now I accelerate, well, I'm adding that same force to both of them in the same direction. So when I subtract those torques, they just cancel out because they're pointing in opposite directions. Okay? So we have that cancellation when we're talking about the torque. They're pointing in the same direction, so they cancel out when we look at their torques. Okay? So we only need to modify the condition for force. So let's do an example of that. Okay. So, much as we've just been talking about, we're going to imagine that we have a truck. Okay. This truck is accelerating forward, getting up to speed. And inside the truck, we have a block. Okay? In the problem in the book, it says a block of marble, mass M, height H, length L. Okay. So, the truck carries a uniform block of marble, mass M, height H, and square cross-section, edge length L. What is the greatest acceleration the truck can have without the block tipping over? So this block is pretty stable, right? It's a big heavy block of marble, but eventually if I accelerate my truck fast enough, it's going to tip over. So we want to use our powers of physics to figure out how fast we can accelerate this truck without it tipping over and shattering this nice marble block, which is maybe going to be part of some rich person's kitchen. Maybe we should break it. Okay. So, if we put the pivot there, also put our coordinate system there. Okay. Now, the book has a really weird explanation for how to calculate this. I like mine because it's simpler and easy to understand. Oftentimes in physics, we're talking about what you might call a littoral condition, when something is just between two situations. So you can imagine we're accelerating, and now we want to do this calculation at that point where this block is just about to tip over, right? As much acceleration as we can get, but it's not quite there yet. It's right on that boundary, right? Littoral is a nautical term. It means between the ocean and the shore, essentially. So the region of not being entirely one thing and not entirely another thing. But you can use that word in other situations. That's your vocab lesson for the day. So just before it's about to tip over, all of the force coming from the truck bed, all of that contact normal force is going to be pointing just at this tip here. Okay, because it's just about to tip over, all of the weight is just at that point. Okay, so that's important because we need now to draw the r vector that points from the pivot to that force, because we'll need to calculate the torque. Okay, so there's going to be a couple other forces, or one other force at work that's important, and that is going to be the force of static friction, right? Which is going to be pointing that way at that same point, where the block is still in contact with the floor of the truck bed. So the rest of the block, perhaps they're still physically in contact, but it's such that all of the weight is just at that one little pivot point. All of the force, I should say, is just at that one little pivot point. Okay, and this force of static, this static frictive force, that's what prevents the block from sliding around, right? It's not just the case that this thing might tip over. It's also the case that as we accelerate, it can just slide in the back of the truck, and since this is a heavy block of marble, it blows out the back of the truck doors and then smashes the car behind you, and then there's chaos. So we're just going to assume that people who loaded this up have thought enough to make sure that this surface can impart enough friction to this block such that it doesn't tip over. Okay. So we know that force of static friction is going to be equal to mass acceleration pointing in the x hat direction. You got x, y. Then we've got that force normal is going to be very similar. It's going to be mass times gravity pointing in the y direction. Okay, pointing up. Okay. So this guy here is essentially our condition for static equilibrium for this non-inertial object, right? If we add up all of the forces, right, as vectors, well, that force normal is going to cancel out with the force of gravity. That's going to be my forces in the y direction. But the x direction, I'm just going to have this one static force. And that static force has to equal mass times acceleration of the center of mass. With now this a, I've moved that, or rather taken the vector component out because I know it's going to point in the x direction. I just have the acceleration. So our condition for static equilibrium for forces for an object in a non-inertial reference frame gives us this equation here, which gives us a value for the force of static friction on this object. Okay. So now what remains to do is calculate the torque. So we'll just call torque 1. That is going to be equal to R cross the force of static friction, okay, which will be, easier if I just do this, which will be minus h over 2 mass times acceleration y hat cross x hat. My computer's making all kinds of beeping sounds. I'm going to stop that. I'll just pause, and then you won't see the interruption. Okay, so sounds off from the computer now, so no more beeping. Okay, so that r vector, that is pointing from pivot down here. Okay, but the only component that's important is going to be that y component, this guy here, right? This guy here. I hope I haven't been standing in front of the board too much. So the only component that's going to be important is going to be this guy here, which is going to be half that h there. So I got h over 2, right, in the negative direction because it's pointing down, mass times acceleration. Okay? And then I have a y cross x for the negative y direction of the y component of this vector, and then the x component comes from the force of static friction. So we're going to get h over 2 ma, and now I'm dropping the vector because sorry, this is tricky, that r cross f, right, points out of the board. So everything's going to be pointing into or out of the board, and we can just see whether it's out of the board if it has a plus sign, right, positive z direction, or into the board would have a minus sign, negative z direction. So it's just less cluttered not to rewrite all of those z hats because they're all the same, up to negative signs. And now we have one more torque to worry about. The torque provided by this Fn here, right, that counteracts the force of gravity. So we have r cross Fn, same r vector, right, and now we're going to have negative L over 2, I'm going to write this on another line, negative L over 2 mass times gravity, right, pretty much the same thing over here is happening over here, except now this guy's not positive x, this guy's negative y, right? But then the only component is, of course, the perpendicular component that's important, right? So now instead of having h over 2, we have L over 2 because this distance here is L. So you have negative L over 2 mg, and we have this one is going to point into the board. So then when we want to add up all the torques, right, we end up with h bar over 2 ma minus L over 2 mg. So now we can find the acceleration just by algebraically solving this, because of course this guy needs to be equal to 0. So we have acceleration equals L over h g. Can we see that? Yeah. This board looked bigger in the picture on Amazon, but it should be sufficient for us. Okay. So if you have any questions about that, go ahead and ask on the forum, but hopefully this problem is pretty clear. I guess what I'm doing, I'm starting drawing real big up here, and then by the time I get down here, it gets small. I'll get better at it as time goes on. Okay. So there's one thing more I want to talk about before we end today's lecture, and I'm just going to sort of mention this briefly. For those of you who this is important for, we'll learn more about it when you get to your class on statics. But the next thing I want to talk about is stress and strain. Okay, so one thing we need to worry about when we're trying to design objects that stay still or don't break, right, is whether or not they're going to be moving around, of course, right? If that bridge rotates like this, of course that means that bridge collapses because of some unequal torques on it. But the other thing we need to worry about is the components of the thing we're building. Are they physically strong enough to take those torques, to take those forces, to be able to support the system, right? So if we build a bridge out of some inferior material, maybe I design it really well and all the forces and torques cancel out in just the right way, but the material itself isn't strong enough to withstand those forces, and it just breaks or whatever, or deforms to the point where it's no longer useful and dangerous. Okay, so there are two ways to characterize the forces on an object which would tend to deform it, right? Essentially, all objects are elastic, but some are more elastic than other. So these two ways we characterize the forces on an object that's trying to deform it are strain and stress. Okay. So imagine we have some object. I will draw it down here. For simplicity, it's just a cylinder of some material. We're putting some force on it at either endpoint. This force is applied over some area on this side of the object, and the object itself has some length L. Okay. So the strain on an object is the delta L divided by L. So we take some rigid object, say this eraser, right? We put some forces on either side of it, and my eraser basically has zero strain from me pushing on it with my hands, right? It's not changing in length at all with respect to L, right? Maybe if I have an object I can squish, maybe a loaf of bread, but I don't want to squish my bread. Hello. So I got my pillow, right? I compress it, right? This object is taking a lot of strain because that total length is whatever it is, but then I'm able to compress it some significant fraction of its total length, right? It's undergoing a lot of strain because that delta L, the amount it changes, is quite large. The other definition is stress, which is how much force I'm applying over how much area, essentially the pressure that object is under. Okay. So, what if I apply a force to an object and I make a plot of the stress versus the strain? Okay. So, you can imagine that the state of any system at any particular given force, so both of these things are going to be functions of force, the state of some given system at some given force is going to be a point on this diagram, right? And it's going to have some amount of strain, it's going to have some amount of stress that's being put on it. So if we start from zero force and increase and increase and increase, we see a linear relationship. Okay. There gets to be some force on that object. The force increases, which of course linearly increases the stress. And for most objects, right, the strain is going to increase according to some proportion. Right? How much it increases depends on the characteristics of the object. So I might also have, as I'll take advantage of having multiple colors, I might also have it working like this, depending on the object. But we're going to continue to follow this black grid. So increasing the force and force and force, and I'm increasing the strain and the stress linearly. Okay. Eventually, this object will hit some limit called proportional limit. And this linear relationship stops. Okay. Now what we get is some other kind of behavior that's not linear. So if you imagine, for example, I've got a piece of taffy, right? I'm going to be able to pull on that taffy, and for a while there's going to be a linear relationship between strain and stress. But if you've ever pulled on pieces of taffy, eventually it just gets much easier to pull it apart. So that's when you've hit the proportional limit, where I no longer have this increase, or this linear relationship between the strain and the stress. So perhaps that strain, how much delta L I get when I'm pulling on that taffy, maybe that now is going up at some faster rate compared to how much stress I'm putting on it. Right? And this is called the point where this stops. It's called the elastic limit. And then I proceed until I eventually hit a point where the object breaks. And that's called the fracture point. Okay. So obviously when we're building a bridge, we don't want to get anywhere past this proportional limit, right? Because we don't want a regime of new behavior, and then we certainly don't want a fracture point. So if I continue with my taffy analogy, as I pull a taffy apart, eventually the taffy just breaks. Okay? And the structure of how these points are laid out depends on the composition of the object, and that's sort of beyond what we're going to be doing in this class. I'm just really mentioning this stuff just so you have seen it and see how these concepts are interrelated. We're not going to spend a lot of effort on this, but I will mention one more thing, is that before we hit the proportional limit, another thing that might be important is which one of these stress versus strain lines we follow, right? If we want something to be very rigid and have very low strain, right, of course we want to have one of these lines that's going pretty close to this x-axis here, this stress axis. So the slope of this line is important, so it gets its own name. This is Young's modulus. And that is given by the Greek letter upsilon. A very rare Greek letter. Very special. And that's just the stress over the strain. Okay. Which then is just FA, or excuse me, F divided by A divided by delta L divided by L. Not really a way to simplify it. Okay. So that's Young's modulus. Essentially how hard or how stiff an object is. Okay, so that's all I wanted to talk about today. Sorry this lecture is coming a day late. I didn't have the opportunity to record it yesterday while it was still daylight out. I don't think you'd be able to see very well what I was writing once it gets dark in here. I've got lights, obviously, but they're maybe not bright enough that you can see this clearly. Okay, so hopefully this new lecture format's a little better than it was before. If you found this difficult to follow for any reason, more difficult than me writing on a piece of paper with the camera above my hand, please let me know, and I'll try and fix those problems. Okay, hope everyone's doing very well, and I hope I hear from you soon. Of course, you saw the other email, hopefully, that told you got a new homework assignment, so please get to work on that, and everyone have a great week. Talk to you soon.